welcome you at the Technical Forum for the 4th day here at the group exhibit Hydrogen and Fuel Cells 2013. Please have a seat. You're really invited to have a free drink here on the house. My name is Kirsten Larsner and I'm your moderator here at the Technical Forum for the day. I'm pleased to give you some information about the day. Here at the Technical Forum, nearly all half an hour, a new and interesting presentation will be. The day's program will close at 4:30 by presenting the program Smart City. Get an insight into the concepts of the sustainable cities and their implementation. But now let us enjoy the presentation by Cella Energy. The topic hydrogen storage without the high pressure by the research scientist Dr. Tom Headen. Give him a big hand, please.
Right. Okay. Hello, everybody. Thank you very much for coming along. I'm going to, first of all, give a bit of introduction to Cella Energy. This is our first time here at the fair, so you probably want to know a bit about us. Obviously, talk about our technology and our key IP, and then what applications we're targeting our material into. So, to give you an overview of Cella Energy. We're developing safe, low-cost hydrogen storage without high pressure for use in power systems mainly, so for transportation fuels and for battery power sources. We have some fundamental IP in this specific material on how to make it work practically in an application, and our model is to license this to third-party manufacturers. There is obviously potentially a huge market opportunity over the next 10 years. So to give you a short history, it's short because we've only been going 2 years, but research began in this area in 2007 at the Rutherford Appleton Laboratory in the UK. That's pretty much the largest research institution, government-backed research institution in the UK. It's where we house all the bits of equipment you only want one of per country. So from a research grant, this material started to be developed. Is this a pointer? Oh. Then in 2011, so 2 years ago, Cella Energy was formed to develop some of that intellectual property and develop the materials. We have labs based in just south of Oxford in the UK at the lab, and recently, last year we opened a lab at the Kennedy Space Center in Florida. Our focus at the moment is on diesel emissions abatement, zero emission vehicles, longer lasting batteries. We have really great academic links to the UK, to Oxford University, University College London, and in the US to the University of Central Florida. So this shows our board of our company, and I put this on just to show, it kind of explains the history of the investment in our company. Our CEO started the company, has a lot of expertise in fuel cells and comes from a fuel cell background, but realized he couldn't really get much further without a good way of having useful energy storage, hydrogen storage, sorry. Our chair is Brian Sanderson, he's an ex-CEO of BP Chemicals, so obviously that's very useful for us. And our key investors have been Thomas Swan, who are a chemical company based in the UK, and Space Florida, who are like a regional development agency for Florida. So essentially, so that's one of the reasons that led to us opening a lab in Florida. So why are we here? Why are we looking to make a safe way to store hydrogen? The world population is growing rapidly. Demand for energy is rising even faster, and yet we're committing ourselves to reductions in CO2. I mean, we all know that's why we're all here. So the Department of Energy in the US did a lot of focus on automotive fuels, new automotive fuels, new ways of storing hydrogen. There was a big research program on it, and they had four kind of main targets for the material. It's got to have a similar energy density to petrol or gasoline. Has to operate close to room temperature and ambient pressures. It has to release and absorb hydrogen quickly. And lastly, they thought of it's got to be cheap. You've got to be able to afford it. I mean, that's rude, but that's a very technical way of looking at it and not really taking into account whether consumers are actually going to make the change from the current technology. So Cella's aims are slightly different. First things first, it must be safe. Then it must be cheap, it must be affordable. Importantly, it must require minimal changes to the infrastructure. Large, expensive changes to infrastructure put a prohibitive cost on introducing a new technology. And the performance must be good. It's got to be good enough. So that kind of gives the base of where Cella's coming from. A little bit more about the technology. This is a technology forum. So this is our base material for our first generation material. This is the base hydride we use. Some of you may have heard of it. It's ammonia borane. It's one of the two hydrides that came out of the big DOE program that they looked at. They looked at a whole load of different hydrides and kind of narrowed down to just two, and this was one of them. It has a very high hydrogen weight percent, 12 to 14 weight percent of hydrogen. That's one of the highest amongst the hydrides. And it releases its hydrogen at fairly moderate temperatures. So you get half of it out between 80 and 110 degrees C, and the next half between 120 and 180 degrees C. But it does have some issues. DOE still like to, despite those issues, one of those that its melting point comes just before its hydrogen release. So I'll show you some pictures later, but that leads to problems. It also, especially at the more moderate temperatures, the kinetics can be quite slow. So what have we done at Cella Energy to make ammonia borane a much more viable material? We make polymer hydride composites, and that eliminates these undesirable qualities of the material. It remains solid when you heat it and you release hydrogen. Certainly at the moderate temperatures, it speeds up the hydrogen release. And you have a polymer layer that can protect the hydride and from water vapor. One thing I forgot to mention actually was that the material itself, ammonia borane, is actually one of the safer hydrides to handle. It's safe to handle in air compared to a lot of other hydrides that aren't. But the polymer here provides just that bit of extra protection. So this demonstrates quite neatly what happens to neat ammonia borane. That's the picture on the left. If you heat it, I think this to about 120 degrees C, it just foams up the test tube. You make our material, that's ammonia borane polymer composite, and you're left still with a solid piece. It remains in one piece. I also mentioned about it increasing the kinetics. For neat ammonia borane at 85 degrees C, you've got this incubation time, which is up to 2 hours long before you actually start to release hydrogen in any significant quantities. By forming this composite, we eliminate that incubation time. So where have we got to now? We've been going for 2 years. Oh, sorry. Is that better? Okay. We've been going for 2 years, and we've further improved the material in that time. We've gone from 3.5 weight percent to 8, or even to 10 weight percent now of hydrogen in our material. Obviously, that's a bit lower than in neat ammonia borane, but we have a bit of polymer in there. We have developed new materials production methods that have taken up the scale that we can produce this material by orders of magnitude, and all the processes we're using are very scalable. Obviously, if you want to go for big markets, you've got to be able to produce ton quantities of this, and we're confident that there's a clear roadmap to be able to do that. And now we've got this base first generation material developing various prototypes and application concepts for it to be used in real world settings. One of these is for automotive. Some of you may already have been to our stand. If you haven't already, I suggest you come. It's just around the corner there, and that's for using a flowing pelletized fuel system based on our material in an automotive application. So the idea there is you have our material in small beads. I mean, I've already said that they, as you heat them, they remain as solid and as small beads. And you have them in one half of a tank. You flow them in portions into a hot cell where you heat them up. You then release the hydrogen once you've heated them up, and you can use that hydrogen in a fuel cell. And then once the hydrogen's released, the spent beads go into the other half of the fuel tank. And you can do clever things like have a movable membrane so that you're not doubling up on volume and things like that. Now, obviously, we want to make sure that this system is going to be viable. So we've done some calculations on the potential system performance based on some assumptions, and we're coming up with similar energy densities and specific energies to high pressure hydrogen, which meets the US DOE targets, the current targets. We commissioned an independent study using, I don't know if you're aware of it, but there's this thing called the GREET analysis, which has been developed at the Argonne National Labs to provide a common way of generating a well-to-wheel analysis for CO2, grams of CO2 per 100 kilometers. And obviously all the onboard emissions are zero. There's no tank-to-wheel emissions. All the emissions are in the well-to-tank for our system. And we're coming out lower than high-pressure hydrogen in this model. The important thing about the system is we don't have to use high pressures. That means our tanks can be irregularly shaped, and we can move pellets around into irregularly shaped tanks. So these pelletized materials, one of the key things for us is that it really minimizes the input costs. You can use similar equipment that already is used on fuel station forecourts. It's also a familiar customer experience. You can imagine what you'd have is a pumping system that instead of just putting fuel in, you'd be pumping beads in and taking them out again. And that would only take a few minutes, so it really wouldn't change that customer experience. And it's safe and simple to use. There's no high pressures. So I've talked a bit about the application in a kind of zero emission vehicle. I want to talk a bit more about more near-term applications in diesel emissions abatement and longer duration batteries, where we're already kind of cutting metal and making prototypes. So as a kind of entry into the automotive market, we're looking at introducing augmenting diesel, with a small amount of hydrogen into an IC, into a diesel engine. This can improve your emissions, reduce your NOx and particulates, and increase your efficiency. So we're working with some automotive partners as part of a partially government-funded project, where we're building a lab-based prototype of this system. We're already making the first parts right now, and we'll be demonstrating them later this year. We're also obviously interested, our material stores a lot of hydrogen, and if you have a fuel cell there, you're storing a lot of energy. It's a battery replacement. So as a near-term entry into the market, we're looking at niche markets where you really need a high amount of energy storage and are willing to pay a premium price for it. Obviously one of those is in military applications. We have a partnership with L2 Aerospace, a company in Florida, to develop a system for a UAV that will provide 3 times the flight duration. But there are other markets, such as working on a cartridge for a business traveller, and we also have links to aerospace as well. So this is really explaining where Cella sits and what we do and how we make sure we, right from getting the raw materials out of the ground to producing products, how we're helping to make that work. So the ammonia borane starts with mining boron. And we already have some links with those companies there. Importantly, that ammonia borate needs to be made, and obviously for future use needs to be recyclable. Need to be able to take it away to a chemical plant once it's been used and remake it back into the ammonia borane. So we have a partnership with a large chemical company that's one of the largest suppliers of ammonia borane, and they're helping us scale up that both the raw materials production and then also the recycling. Then we sit in the middle. We develop the materials, make the materials, and for our first generation material are looking for applications in longer lasting batteries and reducing diesel emissions. We're continuing to improve our material, and for the second generation material and materials system, we'll be looking to make zero emission hydrogen vehicles. So what's our timeline? Spring 2013, that's now. We've made the material, we have our first generation material. We will be developing the prototypes over the summer. Hopefully when I get back, some of the parts will be there waiting for me. And we'll be doing some lab-based demonstrations by the end of this year. We then want to do some field trials in proper vehicles and in proper situations next year. Okay, so thank you very much for listening. If you have any questions, either ask them now, or if you want a more detailed discussion, come over to our stand E69/1, which is just around the corner. Okay, thank you very much.
Thank you very much, Mr. Headen, for this interesting and very informational presentation. Are here any questions in the audience right now? So maybe, yeah, like you mentioned, it's better to speak personally at your booth. Yeah, it would be better for you. Okay. So if you have any questions later on, or you like to discuss a topic more in person and detailed, you can find Mr. Headen at the booth here, right? Seen in the flat screen. You're here all until tomorrow?
Yes, I'm here until tomorrow.
Okay. So, thank you very much, Mr. Headen.
Thank you.
Give him a big hand, please, again. And we will continue our program after a break of a few minutes with IT and Power, with the topic high power density fuel cells for automotive applications. Have a seat, please.